Welcome back to another Forge College Explainer. So if you've been following along with our From EVM to SVM track, you know we've been deep in the trenches of Ethereum to Solana transitions. Last time, we tackled the abstract math behind ERC-4626. But today, we're looking at designing Solana vault state and tokenization. We're taking that theoretical whiteboard and translating it into a concrete architectural blueprint. Think of this as the moment we finally stop arguing about how the house should look and actually start pouring the foundation. By the end of this explainer, you're going to know exactly how to structure your accounts, track your shares, and tokenize your vault, all without pulling your hair out or, accidentally vaporizing anyone's funds. Let's get right into it. Okay, here's our game plan for today. We'll start with the blueprint to translate ERC-4626, then look at the bonk, safe, and ledger models, figure out how to hand out hotel keys, conquer fixed-point math, map out the deposit and withdrawal flows, and finally, look at future-proofing the whole shebang. Section 1. The blueprint ERC-4626 translated. We really need to map this out up front, because on Solana, resizing accounts later is a migration nightmare that you desperately want to avoid. So the absolute centerpiece here is the program-derived address, or PDA. You can think of this as our strict lock manager. Now, in the EVM world, smart contracts naturally hold their own funds, right? But on Solana, programs are completely stateless. So giving raw key pairs the power to control your vault's assets is, well, it's literally like handing the bank's master safe combination to a random guy on the street. No way. A PDA ensures your program's code is the one and only gatekeeper. Section 2. The bank safe and ledger. Let's break down how we split up the heavy lifting between physical assets and mathematical claims. This concept really illustrates a huge paradigm shift. On Solana, we strictly segregate duties. First, we have the bank safe. This is your custody SPL token account. It does one thing and one thing only. It holds the money. It knows absolutely nothing about math or shares. Then we have the bank ledger. This is your custom program-owned vault state account. It acts as the master ledger, tracking every single claim, total assets, and total shares. So basically, the safe holds the cash, and the ledger holds the math. Now check out how compactly we can pack this bank ledger. We've got our versioning, plus public keys for the PDA, the asset mint, and the receipt mint, but pay special attention to total assets and total shares. We allocate 16 bytes each so we can use U128 integers. This is absolutely crucial because it completely prevents overflow when you're dealing with massive numbers and fixed-point math. All in, this entire core structure sits at roughly 200 bytes. That keeps your rent exemption costs incredibly low while giving you a rock-solid ledger. Moving to Section 3. Hotel keys and minting rules. So we have our safe and our ledger, but we still need a way to hand out receipts to users without losing our minds. I want you to think of receipt tokens as automated hotel keycards. When you deposit assets, the vault issues you a keycard. By making the receipt mint an entirely separate SPL token, we actually get to leverage Solana's battle-tested token program. Only our PDA, lock manager, can securely issue or destroy these claims. And here's a quick pro tip for you. While it's not strictly mandatory, aligning the decimals of your receipt token with your underlying asset token, that is going to save your front-end UI developers from a massive caffeine-fueled headache when they try to display exchange rates later. Section 4. Fixed-point math and scaling. It's time to tackle the one mechanism that terrifies most developers: doing math on the blockchain without accidentally vaporizing the protocol's assets. Here's the thing. Solana doesn't play nicely with decimals in smart contracts. So what do? We use a scaling factor, like 1 billion, for example. You can think of this as the absolute smallest, most annoying little coin the bank will officially track. By multiplying everything by this massive scaling factor, we keep our precision totally deterministic. We do all of our asset-to-share conversions using pure whole integer math, no floating points, no unpredictable rounding glitches. And this formula is your golden rule for integer math. It solves the classic first depositor problem. You see, when your vault is brand new and total shares are at 0, dividing by 0 will just crash your program. So for that very first brave pioneer who deposits into the vault, we simply take their assets and multiply them by our scaling factor to set the baseline ratio. From that point forward, everyone else's shares are calculated based on the running ratio of total shares to total assets. But division gets messy, which brings us to your cashier rounding policy. Let's say a withdrawal calculation determines a user is owed 2.999 tokens. What do? Well, you have to consciously choose to either floor the output down to 2 or seal it up to 3. Standard practice in DeFi is to strictly floor asset outputs on withdrawal. I know, it might cost the user a fraction of a cent, but it ensures the bank doesn't over-disperse and slowly bleed itself into bankruptcy over millions of transactions. Section 5. Deposits and withdrawals flow. Knowing the state is one thing, but stringing it all together into instructions is where the real magic happens. For deposits, the logic flows logically step by step. First up, we cryptographically validate that the accounts passed in actually belong to our vault. Second, we run our integer math to calculate exactly how many hotel keys to issue. Third, we pull the user's assets into our custody safe via a cross-program invocation, or CPI. Fourth, we use another CPI for our PDA to mint the receipt shares to the user. And finally, we update our master ledger's totals. The strict order here is absolutely vital, guys. You never, ever mint the shares until the asset transfer has completely succeeded. And the withdrawal flow? It's the exact reverse. After validating, we calculate the assets owed using that flooring policy we just talked about. Then, the PDA gatekeeper uses a CPI to permanently burn the user's hotel keys. Only after those receipt shares are destroyed do we execute the final CPI to unlock the safe and push the underlying assets back to the user. Burn first, transfer second. This prevents those nasty reentrancy nightmares and ensures the ledger always reconciles. All right, Section 6, future-proofing your vault state. Let's talk about padding our architectural blueprint so we don't have to demolish the whole building a year from now. Remember that 200-byte ledger we looked at earlier? We're actually going to purposefully oversize that account to 512 bytes when we initialize it. By allocating an extra 64 bytes or more as a reserved extension block, we give ourselves some much-needed breathing room. You can treat those extra bytes like blank pages in the back of a physical ledger. If you decide next year to add withdrawal fees or an emergency pause flag, you just write to those blank pages. Skip this step, and adding a single new parameter later will force you into a highly complex, terrifying state migration. A quick, absolutely crucial point on security here. Your PDA is generated using seeds. Maybe it's a string that says Vault Authority mixed with a vault's public key. Remember that changing your seed scheme in a future program upgrade is literally like unexpectedly changing a physical safes combination in the middle of the night. You will permanently lock out your own legitimate processes, so keep your seed design minimal and rock solid from day one. And just like that, we've reached the end of our architectural blueprint. You now have the state layout, the account sizing plan, and the fixed point math logic to tokenize a vault on Solana safely. This wraps up our explainer for today, but please make sure to visit forge.college to check out the rest of the From EVM to SVM track. In our very next lesson, we are rolling up our sleeves for the minimal Solana Vault guided build, where we're going to write the actual Rust code to bring this exact blueprint to life. But before we go, I want to leave you with this thought. If a single missing byte in your state account can force a total protocol migration down the line, how confident are you really in the architecture of your current smart contracts? Thanks for learning with Forge College, and we'll see you in the next build.